Wow. 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 Good morning. Wow. 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 Oh, sweet kitty. Oh, sweet kitty. Come here. Hope everyone's doing well. Gonna wait until we have at least 15 viewers before I get started. While we're waiting, I'll tell you about an interesting article I saw this morning. Apparently, so there's this chemical compound called phosphine, and phosphine is not produced in great amounts by normal planetary processes. And furthermore, it's unstable in the sun. So if the sun shines on phosphine, the phosphine breaks down. And apparently on Venus, the planet Venus, they've detected phosphine in the atmosphere. And so they're not sure why there's phosphine there. And the fact that it's there at all is indicative of the fact that it must be being continually produced because the sun breaks down phosphine. So if you have phosphine in significant amounts, you know that it has to be replenished because normally you wouldn't find any phosphine. So, and it's also known that simple organisms can produce phosphine. So they're wondering, it's been speculated that it's possible for simple life to sort of be floating in the atmosphere of Venus. And so that the discovery of phosphine sort of points in that direction. So it's kind of exciting. Hello, everyone. Going to wait for a couple more viewers before I get started. Hello. Sup. Bam, we're at 20 viewers. All right, I'm going to get started. Hello, everyone. Make sure you do your daily attendance. I hope you had a really nice weekend. My weekend was spent mostly inside, trying to avoid all the wildfire smoke. But I was very productive, so that was nice. I want to remind you that your first assignment was due on Friday. So it's not it doesn't give you a hard deadline, I don't think. So it's not like the assignment disappears after the due date. So if you forgot to do that for some reason, go ahead and submit that as soon as possible. Okay, so let's go ahead and get started. The first thing I wanted to do today is simply review what we did last time. So last time we talked about position time graphs. Okay. So a position time graph has x on the vertical axis and t on the horizontal axis. Okay. And maybe a position time graph looks like this. If you have a linear portion, that slope corresponds to velocity. Okay? Velocity is slope of a position time graph. If you see bendiness in the graph, bendiness is acceleration. Okay, so that is a position time graph, and we did some problems. We also introduced a velocity time graph. Okay, and velocity time graphs have a different interpretation. If you have a velocity time graph that looks like this, the slope is acceleration. So I emphasized to you that it is critically important that you read the axes of the graph so that you're not confused, so that you know what slope means, basically. Okay? So we got to be careful about that. Always, always read the axes. Okay, so that's the review from last time. And now I would like to talk a little bit about a concept from math called area under the curve. Okay. So the area under the curve is the area between the graph and the horizontal axis. Okay, the area between the graph and the horizontal axis. So let's say I have some axes here, and then I'm just going to draw a random graph. So maybe something like this, like that. Okay. The area under the curve would be the space between the graph and the horizontal axis. So it would be this space right here. Okay. So what do I want to say about that? Yeah. Now, if the graph goes below the axis, then we don't shade down to the bottom because it's the space between the graph and the horizontal axis. So now the horizontal axis is above the graph, so we have to shade up. Okay? And then now the graph goes above again, so we shade that space. So this is the concept of area under the curve. And it's just whatever that area is equal to in square meters or what have you. Any areas that are above the horizontal axis are positive. So those are positive areas. And if the area is below the axis, it is a negative area. Okay? Now, it is possible to show that if you have a velocity time graph, so now keep in mind that I have like 40% of the time that I would normally have with you this year because I'm seeing you for 1 hour twice per week instead of 1 hour 5 times per week. So normally I would explain this in a little bit more detail, but I'm not going to just because of the amount of time we have. However, if you would like to learn more about this, please come to talk to me during office hours and I can explain why this is true. But there's a nice little fact, which is the area under the curve of a velocity time graph is equal to the displacement. Okay? So we can calculate the displacement from the velocity time graph, okay? So this area right here is displacement, okay? So we have, when we're talking about motion graphs, we have 4 key facts, okay? So if it's a position time graph, slope equals velocity, bendiness equals acceleration. And if we have a velocity time graph, slope equals acceleration, and the area under the curve equals displacement. Okay? So these are our key facts for motion graphs. So let's do an example. All right. Let's suppose that I have a velocity time graph. And so the velocity is measured in meters per second. The time is measured in seconds. And what if it looks like this? What do I want to make it look like? I think I'm back. Sorry about that. I'm usually monitoring the connection in the live stream. Sometimes I don't notice if it cuts out. So yeah, thank you for putting that in the live chat so that I notice. Okay, so all I did was I drew the graph, and I'm going to pick some coordinates here. So I'm going to say that this is 3 seconds, and that is a velocity of 10 meters per second. And I'll say that that is 9 seconds. And I'll say that this is 11 seconds, and the velocity goes down to minus 15 meters per second. Okay? So I'm going to ask 2 things about this. I'm going to say, first of all, first part of this question is, what is the acceleration at, let's say 5 seconds. 5 seconds into the journey, what is the acceleration? So first of all, what I want to do is I want to notice that this is a velocity time graph. Okay? This is a velocity time graph. So that means that to get the acceleration, I need to do the slope. See, I have a velocity time graph, and I can see slope is acceleration. This graph is made up out of 3 line segments: segment 1, segment 2, segment 3. So the question is, which segment corresponds to 5 seconds? And 5 seconds is between 3 and 9. So I'm talking about the slope of this segment. Okay? So I can see that the run is from 3 seconds to 9 seconds. So the run is 6 seconds. And the rise, it goes from 10. See, there's the velocity of 10 down to 0. So that's a rise of minus 10 meters per second. So that gives me a acceleration of minus 1.67 meters per second squared. That is the acceleration at 5 seconds. If I said, what is the acceleration at 1 second, you would find the slope of that first segment. If I said, what's the acceleration at 10 seconds, that would be the slope of that line segment. Okay, so the time is really telling you which line segment you want the slope of. The next part of this is, what is the displacement? For this journey. Okay, I have a velocity time graph. Okay, have a velocity time graph. And so if I want displacement, that's the area under the curve. So I'm going to be calculating the area under the curve. And I will always, so if you took a calculus class, they would give you, complicated functions, but mine are always going to be simple. They're going to be made up out of straight lines and straight line segments, so that you don't have to know any calculus to do the area under the curve. So I can see that the displacement is the area, and I can see I've got basically two triangles. I've got this triangle right here, and I've got this triangle right here. This triangle is negative. Okay, so I have the area of this triangle minus the area of this triangle. Okay. Now, what is the area? The formula for the area of a triangle is 1/2 base height. I'm assuming you remember that. So I'm going to have a 1/2 base height for this triangle. Well, the base of that first triangle, it goes from 0 to 9. So that's a base of 9. The height of the triangle, it goes from 0 to 10. So that's a height of 10. Now I'm subtracting the area of the second triangle, 1/2 base height. The base of this triangle is from 9 to 11, so that is a base of 2, width of 2. And the height, it goes from 0 to 15. So you might say the height is negative 15, but I already have the negative right here, so I'm going to say that the height is just 15. Okay? And so this is the displacement. So that's 45 minus 15. That's a displacement of 30 meters. So that's how you would do that. Okay? So I hope that makes sense. That's if you end up taking the IB exam, I can guarantee you that there will be a question that requires you to know whether slope and area under the curve of a velocity time graph. Okay, it shows up in pretty much every IB exam. Very good. So we're going to go ahead and move on from motion graphs to the next part of kinematics. And we're going to spend the rest of today and also Thursday's lesson on this. Okay. And so I'm going to talk to you about what's called uniformly accelerated motion. Okay? Uniformly accelerated motion means that your acceleration is equal to a constant. This is not, it's often the case that the acceleration is constant, but it's not always the case. If you're in a car and you're pushing the gas down, you accelerate, and then you take the gas, you let up on the gas, you might still be accelerating, but accelerating at a less severe rate. Okay? So depending on, your acceleration can change. If we're talking about uniformly accelerated motion, it means that the acceleration is constant. Okay? What does that mean? If you were to draw a velocity time graph for uniformly accelerated motion, tell me what that would look like. Put it into the live chat if you know what a uniformly accelerated velocity time graph would look like. So while I'm waiting for a response, the video might look a little bit fuzzy today. My internet is definitely fluctuating a lot this morning. I don't know why it is, but it's fluctuating. I'll try to write bigger for the rest of this lesson. So if you have uniformly accelerated motion, your velocity time graph looks like a straight line, okay? Because if the slope of that line were to change, that would mean that the acceleration changed. So under the assumption of uniformly accelerated motion, it's possible to prove 3 equations, okay? And these are called the kinematics equations. Again, normally I would try to derive these equations, but we just don't have the time this year with the 2 days a week. If you would like to see the derivation, I would be more than happy to show you during my office hours from 1:40 to 2:30 this afternoon. So what are these equations? There's equation 1, which says displacement equals v naught t plus 1/2 a t squared. So delta x is the displacement. V naught is your initial velocity at the beginning of the acceleration. T is the time that you accelerated for. And a is the value of the acceleration. So this is t squared. Only the time is squared, the acceleration is not. Okay, so that is the first kinematics equation. Second kinematics equation says v final equals v initial plus a t. So v sub f is your final velocity. V initial is your velocity at the beginning of the acceleration. A is your acceleration. T is your time that you accelerated for. All right. And then there's a third kinematics equation that is the following: v final squared equals v initial squared plus 2a delta x. So one of the things I want you to notice here is that each of these kinematics, so you can think about these kinematics equations as tools that allow you to calculate something about motion, either a velocity or a displacement or an acceleration. Each of the equations is a different tool. It allows you to solve, they're all saying the same thing. They're all describing uniformly accelerated motion, but they're expressing it in different ways. And we know that by looking at the variables involved. What are the variables in the first kinematics equation? We have displacement, initial velocity, time, and acceleration. Okay. In the second equation, this equation involves final velocity, initial velocity, acceleration, and time. So notice how this second equation does not have displacement, but it does have final velocity. So it's a different tool, okay? That's going to allow you to unlock the solution to a different type of problem. And then the third equation, has v final, v initial, acceleration, and displacement. Okay, so each of these equations uses 4 variables, but it's a different set of 4 variables for each equation. Okay, it's all describing the same motion, but it's describing it from a different point of view. All right, so let's use these equations in some example problems. Okay, so we'll go over a couple of examples. Let's suppose a car is traveling at 700 or 70 meters per second. That's really fast. 70 meters per second is like super duper fast. But, you know, that's over 150 miles per hour. So this is a sports car. A car is traveling at 70 meters per second. It applies the brakes, or I should say the driver applies the brakes, decelerating at 12 meters per second squared, decelerating to a stop. So as you know, if you are in a car and you slam on the brakes, in the car doesn't just immediately stop. While it's decelerating, it's still rolling forward, okay? So the question is, how far forward did it roll? Okay? How far forward did it roll? So, what we want to do, first of all, is we want to parse the question for numbers, okay? And figure out what do those numbers mean. The car is traveling at 70 meters per second. That's what the car was doing before it started decelerating, okay? So that must be my initial velocity. So I have initial velocity equals 70 meters per second. It applies the brakes, decelerating to a stop. Decelerating to a stop. That means if you come to a stop, that means that your final velocity must have been 0. So I have that v final equals 0 meters per second. But it tells us more. It says that it's decelerating to a stop at 12 meters per second squared. That's an acceleration. How do I know that? First of all, I know it's acceleration because of the units, meters per second squared. So my acceleration, and because it's rolling forward and it's decelerating, anytime you're traveling in one direction, like say the positive direction, if you decelerate, it's going to be the opposite of that. So it's got to be a negative acceleration. So minus 12 meters per second squared is the acceleration. And then how far forward did it roll? So one of these 4 variables is always going to be unknown. If we know all 4 variables, then there's not a problem to solve, right? So one of the 4 variables is going to be an unknown, and we want to know how far forward did it roll. So we're asking for delta x, okay? So notice how this problem has 4 variables, okay? It has 4 variables. It has the variables v naught, v final, acceleration, and delta x. So look at this list of 3 equations, and which of the 3 equations has these 4 variables in it, okay? So I'll wait for you guys to type an answer into the live chat. Exactly, yeah, it's the 3rd equation, okay? Very good. So what I'm going to do is I'm going to write the 3rd equation, And then in the next line, I'm going to substitute in the known variables. And I'm going to leave the unknown variable displacement. I'm not going to touch that one. I'm just going to leave it as delta x. Okay? So v final is 0. So I have 0 squared. V initial is 70. Plus 2 times the acceleration is negative 12. Delta x. Okay? And then I can simplify this. 0 squared is 0. 70 squared is 4,900. 2 times negative 12 is negative 24. Delta x. So you can see this became a linear equation for delta x. So I can just do algebra and I can solve for delta x. Okay, so that tells me that this car will roll forward 204 meters while stopping. Okay, you might, if any of you are taking driver's ed or anything like that, you know that you're supposed to keep a certain distance behind the person that you're following so that you have enough stopping distance. Okay, and the faster you go, the more space you want to leave between you and the car in front of you. Okay, and that's because the faster you go, the more displacement you're going to have while you're slowing to a stop, so you don't rear end the person in front of you. Okay, let's just do one more really quick example, then we'll switch over to Zoom. Let's say that a drag racer starts at rest and accelerates at 22 meters per second squared for 1,000 meters. A kilometer. Okay, so I live in Laverne, kind of close to the NHRA track, kind of next to Fairplex, and so there's a lot of drag races that go on there in a normal year, and so yeah, so they want to know how much time does it take to do the race. So how much time? Okay, I know the writing is a little bit small. So what do we know in this problem? We know that the drag racer starts at rest. So that means that V initial is 0. Okay, we know that the acceleration is 22 meters per second squared. We know that the drag racer travels 1,000 meters. So that means displacement is 1,000. And I want to know how much time is it going to take. So I have time is equal to question mark. So who can tell me? Type it into the live chat if you know which of the 3 kinematics equations is going to allow us to unlock that problem. I will wait. Yes, equation 1. Very good. So I would use the first equation, and I'll just put the variables in here. We have delta x equals 1,000. Someone said equation 2. The reason we can't use equation 2 is because there's no v final in this set, right? Equation 2 has v final, equation 3 has v final, so we've got to use equation 1. So we have 1,000 equals 0 times t plus 1/2 of 22 is 11. 0 times t is just 0. So we have the time to complete the race would be the square root of 1,000 over 11 seconds. Okay? If this was a little bit fast, we're going to spend our entire lesson next time about solving kinematics equations problems, so don't worry about it. That's my lesson for today. I will see you in the Zoom room. Peace out.